here we go to the final section. That's the equation of state. Okay. Well, the equation of state is just an equation that gives us a relation between the pressure, temperature, and the specific volume. Okay. For the real pure substances, it's very difficult to get a very general equation of state. As a result, we may also include some kind of idealization here. We introduce an idealized gas called ideal gas. Okay. It is an imaginary gas in which there are three criteria. Okay, you need to remember that. First one, all collision between the molecules are perfectly elastic. Perfectly elastic means that during the collision, there will be no loss in the kinetic energy. So when two molecules collide, they just move away with no change in the kinetic energy. The second one, there are no intermolecular attractive forces. Okay, we just neglect those intermolecular attractive forces. The reason is that the particles are moving very fast. Okay, the Ke is so great that the Pe is essentially negligible. And the third thing is that the size of particles are negligible. We do not need to consider the size of it. Okay. And we have a general criteria that a real gas can be approximated as an ideal gas at a low pressure and high temperature. Because at high temperature, then the intermolecular force can be neglected. And for low pressure, it is also the case. Okay, you need to remember this approximation at a low pressure and a high temperature. Okay, low pressure and a high temperature. Okay, after that, we state the so-called ideal gas equation of state. Okay, here is the ideal gas equation. In your high school physics or the university physics you have taken in your first year, you will see the ideal gas equation to be slightly different from this. It should be PV equal to nRT. That's the version that you should see in your high school physics or first year university physics. Okay, but for thermodynamics, especially engineering thermodynamics, we will usually write it in this form. P small v equal to RT. And this R is different from this R. This R is actually the so-called universal gas constant, and it's the constant. For this R, it's called the gas constant. But this gas constant is dependent on different materials. If the materials have different molar mass, that is the mass of 1 mole of substance, then we will have different R here. Because in our table, we usually record R inside the table, so we will use this form very often. Okay. So note that the mass will be equal to the molar mass and multiplied by the number of moles. Okay, or we just write it to be small m equal to big M times big N. Okay, but here in your previous version, we also write the N to be small letter. But in this case, we will write it to be a big letter N. And this big letter M is the molar mass, the mass of 1 mole. Okay, and from this ideal gas equation, we can convert it by several means. We can convert it to this form. This form is also a very useful form. P big V equal to mRT because of the definition of the specific volume. Okay, and here we can also rewrite it to be this mR to become big N times R, and this M multiplied by this R, okay, we will have the universal gas constant. Okay, so we can get our original form of PV equal to nRT. But for this form, it will be difficult to use in our thermodynamic class. So we will usually use this form as well as this form. So okay, remember these two versions. We will use it very often. Okay, and if we have a V bar here, it means the molar volume. The molar volume just means the volume of 1 mole of gas. So by definition, we have this one, and we can also convert it to be in this form. These two are rarely used. The most frequently used ideal gas equation, the format of the ideal gas equation will be these two. Okay, and this universal gas constant is equal to exponent 314 kilojoule per kilomole Kelvin. Okay, and the one thing I need to mention is that if you need to use this ideal gas equation, note that this T is in Kelvin, must be in Kelvin. Okay, otherwise you will have a big error. It's because it's not delta T. Okay, as I've mentioned, if delta T, then the 273 will be gone, so you can use degree C. But here, we need the absolute value, so we need the T in the units of Kelvin. Okay, remember this. Okay, many students would get wrong, okay, because they simply forget that we need to change it back to Kelvin. And also from this ideal gas equation, we can write P1V1 over T1 equal to P2V2 over T2, because PV divided by T just equal to the number of moles multiplied by the universal gas constant. For closed system, we do not have any change of moles, so we just have a PV over T equal to constant. Okay, and if we have two states, then we just give number 1 and number 2. Okay, so let's see some examples.